Hello guys. If you're wondering why I look different, it's because I just got a haircut and I'm feeling great for another USACO problem today. So today we're going to be doing 2017 US Open Contest Silver Problem Bovine Genomics. Farmer John is going to own N cows with spots and N cows without spots. And we're given for each of the cows a genome that is a string of length m. And our job is to find 3 indexes in these genomes that we can correctly identify if a cow is spotty or if the cow is plain just by looking at those 3 indexes. Our job is going to find how many possible combinations of indexes there are in the given input. Without further ado, let's take a look at the sample input. So in the sample input, I have already put all the genomes for spotty cows and plain cows. So our job is just to find 3 indexes. And because there are so many combinations of finding 3 indexes, we're not going to go through every one of them, but we're going to go through some examples. So the first example is, let's just take the first 3 indexes. We're going to take these 3. And when we take these 3 indexes, we're not going to look at anything other than these 3 indexes. We're just going to be looking at these 3 indexes. Okay, so for these 3 indexes, we can see that AAT is a spotty cow, GAT is a spotty cow, GGT is a spotty cow. Okay, and for the plain cows, we have all of them are ACTs. Well, if Farmer John were to just look at these 3 indexes, he would be able to separate the plain from the spotty, because he would just know that every time he saw an ACT cow, it would always be a plain cow, and every time he sees like AAT cow or GAT or GGT, it's always going to be spotty. So we can also observe that between any spotty and plain cows, the genes are never the same. So we see that for plain cow, we only have ACT, and for spotty cow, we have a bunch of other things, but never ACT for both. Okay, let's look at a different index. Let's look at these 3 indexes over here. So for spotty, we have TCC, TGC, TGC again. Then for plain, we have TCC, TGC, and another TCC. Well, we can see that we have many overlaps in this case, because we can see we have a TCC in a plain and also a TCC in a spotty. And if we were to just look at those indexes, we're not going to be able to tell if a TCC is plain or spotty. So if we were to only look at these 3 indexes, we would not be able to tell which one is spotty, which one is plain. And it turns out that there are 22 combinations of finding 3 indexes, which makes it able to tell if a cow is plain or spotty. So how do we actually go about solving this problem? Well, for many of my videos, I actually go through the brute force solution first. And so let's just do that. For the brute force solution, we want to try all the possible combinations of the 3 indexes. We can achieve that by doing 3 nested for loops. So if we do 3 nested for loops, we're going to have a complexity of 50 cubed. And then for each of the 3 indexes, we're going to cycle through every cow to see if any of the spotty overlaps the plain. And so that is going to multiply by 500. And if we calculate this, we're going to get 62 million. One more observation is that 50 choose 3 is actually not quite 50 to the power of 3, because we're going to have overlaps if we do that. And so the actual complexity is going to be a little bit lower, which is sufficient for USACO. So how do we actually check if the spotty overlaps the plain, or if any 3 indexes in spotty is the same as the genes in the plane. Well, we can achieve this by making a set. So we're going to keep a set every time we're looking at the spotty gene. So, for example, if we choose these three indexes, we first have TCC. And the way we're going to store that in the set is we're going to make it a base 4 number. Because all we can have in the genes are A, C, G, and T. And so we can map those each to a number. So let's just say A is 0, C is 1, G is 2, and T is 3. So by doing this, TCC would just be 311. And 311, we're going to turn that in base 4 to base 10. So 311 from base 4 to base 10 is just going to be 3 times 16, because this is the 16th place, and then 1 times 4 plus 1 times 1, because that's the 1st place. And so we're going to have a set of integers to store these hashed values in. And so we're going to cycle through all of Spotty, and we're going to hash all of them and put them in a set. Then when we cycle through the planes, we can hash the planes as well and go to the set to try to find if the set already contains that number that we hashed. If that number exists, then that means we have an overlap, and these three indexes are not going to tell us if a cow is plain or spotty. If you guys were wondering why I didn't directly put the string in the set, it's because for Java, strings are their own classes, and it's very hard for them to work with strings. And if you put a string object in a set, that's going to be hard to access later with another string that is the same in value but is different in an object. To get a better understanding of this, let's take a look at the code. So in the code, I'm going to have the N and the M, and I'm going to read in the N and the M over here. And I also have this function called toBase4, which is going to take in 3 integers, and it's going to return the base 4 of those integers. So if we look here, we're going to multiply A by 16 and B by 4 and C by 1, because C is going to represent the 1's place, B is going to represent the 4th place, and the A is going to be representing the 16th place. So this is kind of our hash function. And we're also going to have a vector of spotty and a vector of plain. So this is going to be a vector inside a vector. And the first vector is just going to represent the cows, and the second vector is going to represent the actual genes. So we're going to cycle for I from 0 to n. We're going to read in the string s. We're going to cycle again from 0 to m. And for each j, we're just going to check the string s of j. And if it's going to be equal to a, so we're going to put the spotty ij to 0. If it's c, we're going to put it as 1. If it's g, we're going to put it as 2. And then lastly, if it's t, we're going to put it as 3. And so this basically constructs the whole spotty vector. Now we're going to do this exact same thing for the plain vector. The same for loops. We just switched it to changing the plain vector. Okay, now we're going to try all of the combinations of the 3 indexes. So we're going to first have our result first. And then we are going to have the triple loop. So the first loop, we're going to say I from 0 to m. The second loop, we're going to have j from I plus 1 to m, because we don't want to do I or anything before that. And for the third loop, we're going to just say k from j plus 1 to m. This will basically try every combination, and the combination is going to be I, j, and k. So inside the loop, we're going to first do spotty as we've said before. We're going to add it into a set first. And so we're just going to have another for loop, L from 0 to n. And inside the loop, we're just going to insert the base 4 of spotty L, which just means the lth cal that we're looking at, I, which is one of the combination we came up over here. So that's going to be the gene, the first gene for that cal, second gene for that cal, and the third one. We're going to convert it to base 4, and we're going to put it into the set. And now we're going to check if any plain cows overlap with that. So basically the same thing, converting to base 4, but now we're finding from S instead of adding to S. So we're going to first set our flag to false. Flag is just going to be the result if it's overlapping or not. And in the loop, we're just going to convert it to base 4, similarly to how we did it over here, but we're going to change it to plain cows now. And we're going to try to find if that number is in the set already. If it's not, then we keep going. If it is, that means it's overlapping. So we're going to put our flag to true, and we're going to break out of the loop. Over here, after we've exited the loop, we're going to check if flag is false. If it's false, that means it's not overlapping. We're going to add 1 to result. If it's true, it's just going to keep looping, and I think that is the end of the program. Overall, this problem is one of the easier silver problems because it is just a brute force solution and complete search, which is one of the topics for bronze. But this problem also teaches us to not overthink and always try the brute force solution first. Hope you guys enjoyed this video, and I'll see you in the next USACO problem.